Hello, I'm Dmitry Reznikov, representing the Institute of Machine Sciences of the Russian Academy of Sciences. I'll be talking about the probabilistic description of fatigue crack growth and the assessment of the probability of fatigue failure of structural components subjected to cyclic constant amplitude loading with overloads. The overload here is defined as an accidental high-stress peak that is superimposed on a constant amplitude load history. Such overload may occur due to an operational error, an accidental load, or some specific load regimes. During operations, structural components are commonly subject to variable cyclic loading that includes cycles with increased tension or compression impacts. Many mechanisms were considered to be involved in crack propagation after application of an overload, such as residual stress effect, crack closure effect, crack tip blunting, and strain hardening. However, there is still no general consensus on the relative importance of those mechanisms. The presence of such overload cycles predetermines a much more complex kinetics of fatigue cracks. Multiple experiments show a notable decrease in crack growth rate after the overload. This delay can be described by Paris model that is commonly used to describe the kinetics of fatigue crack in the components subjected to constant amplitude loading. And Wheeler in 1972 proposed a simple model that allows describing this effect. His model is based on the assumption that crack retardation is caused by the large monotonic plastic zone ahead of the crack tip that is induced by the overload. So Wheeler modified the Paris equation by introducing a retardation function phi that is defined by equation 4. The key parameters of the model are the shape exponent omega, the size of the plastic zone induced by the regular loading cycle RPI, and the size of the plastic zone induced by the overload cycle RPOL. According to Wheeler model, retardation will exist as long as the current plastic zone is located within the plastic zone formed due to overload. By increasing retardation function to unity, retardation stops at the moment that the boundary of the current plastic zone reaches the boundary of the overload plastic zone. At this moment, the crack growth rate becomes equal to the crack growth rate before applying the overload. The size of the plastic zone for the plane strain case can be calculated according to equation 5. Equation 3 can be integrated numerically in finite differences. And by integration of the equation 3, we can get a dependence of the crack depth A against the number of cycles n, or the so-called crack growth curve. Then a critical crack depth is determined using the criterion of brittle fracture A, and the condition of the component failure is expressed by the equation 10. In the view of uncertainties, we can introduce a safety factor and rewrite the condition of failure in the form 11. So this is the solution of the problem in a deterministic formulation. We should, however, bear in mind that all the parameters of our model are actually uncertain. We never know the exact values of initial crack size A0, parameters C and M of the Paris law, shape exponent, as well as other parameters such as yield stress, applied loads, geometrical dimensions of the component, etc. In particular, the damage parameters C, M, and Wheeler exponent omega are normally estimated by fitting fatigue test data measured under controlled laboratory environment conditions. Due to potential differences between the test and in-service conditions, there is substantial uncertainties in these parameters. In addition, there is uncertainty in the initial crack size A0 that is estimated during non-destructive testing. Thus, it is better to solve the problem in a probabilistic formulation. In this model, we consider 4 parameters A0, C, M, and omega as probabilistic, and other parameters of the model are assumed to be deterministic. So I have written down equation 6' again and marked the parameters that are considered as probabilistic by the red color. From the probabilistic standpoint, these uncertain parameters are treated as random numbers. The probabilistic assessment is performed by Monte Carlo simulations based on random sampling. It consists of running deterministic assessments a sufficiently large number of times with different combinations of random sampled input data and building a set of crack growth curves. So, using all the available prior information that we can get from literature review or from some laboratory experiments about that certain parameters, we can construct a prior probability distribution for each of the parameters. If the level of uncertainty is quite high, we can choose uniform distributions. We also assume that these parameters are independent and form a joint PDF of these parameters. After that, we have to draw a sufficiently large, say 10 power 6 number of samples from this PDF, or in other words, get a set of combinations of random parameters. Then for each of the combination, we can perform a numerical integration of equation 6' and get a set of fatigue crack growth curves. And for each of the curve, we have to check whether the condition of failure 10' holds or not. After that, the probability of fatigue failure for a current number of loading cycles n can be determined as the ratio of the number of curves in our sample that cross the horizontal line of AC within the specified range of cycles to the total number of curves in the sample. A simple computer code in MATLAB was developed to assess the probability of fatigue failure with accounting for the effect of crack retardation after the overload. Here is the numerical example. We have a pipe with a crack on the internal surface subjected to a cyclic loading with a single overload. These figures show the prior probability of fatigue failure as a function of n. It should be noted that this assessment is a so-called prior assessment. It is based on initial data on the material properties and general statistics on the performance of the structural component in similar conditions and does not account for information on actual performance of the component that can be obtained during technical inspections. As soon as we get data from non-destructive testing of the particular component during its operation, these prior assessments can be updated using Bayesian updating procedures. As I have already mentioned, the damage parameters C, M, omega in equation 6' had been estimated during some laboratory tests, but they are not exactly relevant to specific structural component. Due to the potential differences between the test and in-service conditions, there is a substantial uncertainty in these parameters. And subsequently, there is an uncertainty in crack size A. These uncertainties can be reduced by means of Bayesian inference that provides a rigorous mathematical framework of updating beliefs about uncertain parameters when the results of crack measurement became available. In the final part of my presentation, I will briefly describe one of the possible variants of application of Bayesian inference to assessment of the fatigue failure probability. In the work of Jaideep Karandikar and his co-authors, an original approach was proposed that combines Bayesian updating with the random walk method. The key idea of this approach consists in updating the probability of event that a specific sample fatigue crack growth curve is the true or correct fatigue curve. For each sample curve, the Bayesian rule can be written as equation 13. Here, P' is the prior probability that a sample fatigue curve AG is the true fatigue crack growth curve. All sample curves are assumed to be equally likely. It means that for all sample curves, P' is equal to 1 divided by Mn. L here is the so-called likelihood function that describes how likely it is that the sample curve is the correct curve, given the measurement result at a particular number of loading cycles n. If the sample curve lies near the measurement result, then its likelihood value is high, otherwise it is low. It should be noted that the likelihood function defined in equation 14 does not completely reject curves which differ significantly from the experimental result. It simply yields a small weight value for these curves. As soon as we get the posterior probabilities of crack curves, we can determine the moments of the underlying distributions of uncertain parameters. Here they are defined by equation 15. As we managed to reduce the level of uncertainty in the model parameters, we can further assume that the posterior distributions of uncertain parameters are Gaussian. After that, we can draw samples from these updated Gaussian distributions and construct a posterior set of fatigue crack growth curves. Then the posterior probability of fatigue failure is estimated according to equation 17 as the ratio of the number of posterior sample curves that cross the AC line within the interval from 0 to the current value of n to the total number of curves in the sample. Here is the dependencies of the posterior probability of fatigue failure for two cases of inspection results related to the numerical example considered earlier. Case 1. The size of the measurement of the crack is rather small. Case 2. The size of the crack is closer to the critical value. It should be noted that due to the reduction in uncertainties, the posterior curves are more abrupt than prior curves. For the larger crack length measurements, the posterior curve moves to the left, for smaller crack to the right. And at the end of my presentation, I would like to point out that due to uncertainties, the kinetics of fatigue crack should be described in the probabilistic formulation. And Bayesian procedures should be used to update our probabilistic assessments when new data on the performance of structural components become available. Thank you for your attention.